Good morning, everyone. I thought I would give this a slightly different shot this morning and try to pre-record this lesson. That way you can just rewind and replay things that you want to hear again. Um, let's see how it goes. Okay, I'm going to switch over one of my cameras to today, which is 5.8, day 2. We are doing logistic growth and decay. It is simply an example of where you might see exponential or logarithmic equations. Here is a neat formula, Newton's law of cooling, which you do not have to have memorized or anything like that. If we need you to use any of the logistic equations on the test, they will be provided. So it's really just a matter of you being able to manipulate these equations with the things that you have learned. Newton's law of cooling is kind of neat. It basically says that the rate at which something cools depends on the difference in temperature between it and what we call the ambient temperature. So the larger the difference, the faster things heat up or cool down. An interesting application. My dad is a huge coffee drinker and a big fan of science, and only likes to drink hot coffee once it has cooled to an appropriate level. And being impatient, he wants to find the fastest way for that to happen, whether that's just to sit there and wait for the coffee to cool, and then at the last possible moment, put in the cream, which will cool it even further, or to put in the cream, which will cool it down some, but not enough, and then wait. And perhaps you could provide him with an answer onto which one would be better. And apparently my cat has made a guest appearance. Hi, Glitchy. Okay, so once again, here's that formula. T is the ambient temperature, the constant temperature around. An object is heated to 90 degrees Celsius and then allowed to cool in a room whose air temperature is 25. So 25 is my ambient temperature. Plus, my initial temperature again was 90. So like before, that sub-zero pronounced not, U naught is the initial temperature. They said A naught here and U naught there, but whatever. 90 minus 25. So right there is that difference in temperatures, that 90 minus 25. And e to the k, which my first thing is going to be to figure out what k is. T, and T is 10 minutes. After those 10 minutes, it is down to 75 degrees. So we should be able to solve this formula for K. The first thing that I'm going to do is I'm going to subtract 25 from both sides. I get 50 equals, well, 90 minus 25 should be 65. E to the 10K. Divide both sides by 65. I get 50 65ths, which can be reduced, but we're going to plug into our calculator in just a moment anyway. Equals E to the 10K. My variable that I'm looking for is in the exponent, so I'm definitely going to take the log of both sides. I can take the log base anything, but being a mathematician, I like to take the natural log, and seeing as the base of this is e, it only makes sense. So the natural log of 50 65ths is equal to the natural log of that side. Well, the whole point of doing that is that the 10k comes down. Technically, I have a natural log of e there, but that's just one that I can ignore. Final step to figure out what k is divide by 10. Natural log of 50 65ths all over 10 is equal to k. Okay, from there, I can figure out when it will be 50 degrees. So it's kind of like a part B of this problem. I know that it said part A is the whole dang thing. But I am going to rewrite my initial equation here, my temperature at any time. I am interested in it being 50 degrees, is equal to that ambient temperature plus the differences in temperature, 90 minus 25, e to the k. We have solved for k, but I'm not going to rewrite that mess there. And t is what I'm looking for. So pretty much the same thing, subtracting 25. This time I get 25 equals that 65 e to the k t. Dividing, I get 25 65ths equals e to the k t. Taking the natural log of both sides, a little bit quicker this time, just equals k t. And the natural log of 25 over 65 divided by k is equal to t. We've done the heavy lifting. The rest is just plugging into the calculator. I kind of am going to do it inside out. So I'm going to type into my calculator here. On, clear that stuff. The natural log of 50 divided by 65. Enter. Divided by 10. Enter. And I've got this 0.006. I'm never going to retype anything into the calculator. So now I'm going to do natural log of 25 divided by 65 divided by that answer. And once again, the answer key, very useful, is second negative on this calculator. And when I do that, I ended up with a negative, so that seems a little bit weird, 158.7. I don't know. Let's give that one another shot. Maybe my big fat fingers hit something wrong. So the natural log of 50 divided by 65 was a negative, as you'd expect. It's less than 1. Divided by 10, we still have that negative 0.02 this time. Okay. So natural log of 25 divided by 65, all divided by that answer. And now I'm getting 36.4. I do not know what I hit before. T is approximately 36.4, and it looks like we're doing things in minutes. Just to be clear, in 10 minutes, it cooled to 75, and since it was no longer as hot, it wasn't cooling as fast, so it's going to take a fair amount longer for it to get down to 50. Okay. Really, from here on out today, it's just using that equation or equations like it to do similar things. An object is heated to 90 degrees Celsius and then allowed to cool in a room whose air temperature is 25 degrees Celsius. I'm going to see if I can pause my recording, and I'll give you guys a couple of minutes to give this one a shot. I will put up the answer. Okay, so this is what I ended up with. It seemed exactly the same as the previous problem. We are using that same object. It is just a continued thing. So we had the same value of k and all of that. I will do what I did before and hopefully get it right this time. So I'm going to take the natural log of 50 divided by 65, hit enter, divide that number by 10, hit enter, take the natural log of 5 divided by 65, end those parentheses, and divide by my answer. And I'm getting t to be approximately 97.76, 97.76 minutes here. Okay, before I do part C, what if they put this at 20 degrees? What would be the time? Well, okay, that's even lower in temperature, so it should take even longer, but the air temperature is 25 degrees Celsius. We are never going to get there. Looking either at the mathematics or at just the logic of the situation, when this thing goes on and on and on forever, it's going to reach a temperature of 25 degrees. So really quickly here, remember that T is 25, K is a negative number. If T is a large number, then KT is a large negative number. E to a large negative number is close to 0, and 0 times this is close to 0. 0 plus T is close to, well, T, that ambient temperature, that 25 degrees. All right, next up, Sandy manages a ceramic shop and uses a 650-degree kiln to fire ceramic greenware. After turning off her kiln, she must wait until its temperature reaches 175 before opening it and removing ceramic pieces. I'm going to say that that end temperature is 175. The room is 70 degrees equals, there's my ambient temperature, plus that difference in temperatures. So that would be 70 minus 650. This time we'll get a negative. E to the K, which we're going to have to search around for a little bit, and T. How are we going to find K? Much the same way we did before, by saying 550 degrees is what this thing reaches in 8 minutes. 70 plus 70 minus 650. You guys can't see what I'm writing. There we go. E to the K, and the time was given this time of 8. So subtracting, I end up with 480 equals that 70 minus 650 should be 580. 580, a negative 580. E to the K times 8. When I divide, I'm going to end up with a negative over here, which is problematic. I get 480 over 580. Sorry about that weird 8 there. But it's a negative. E to what power would be negative? None of them. Really, we can just ignore that. Equals E to the 8K, and the natural log of this thing, which we could have reduced, but the calculator will take care of us it anyway, equals that 8K. Let's divide by 8, and I get that K equals the natural log of 480 over 580 all over 8. So now back to my original equation and figuring out the time. I'm going to get 105 when I subtract equals that. Technically negative, but I don't have to worry about it. They should really have an absolute value there. So that 580 e to the k, which we've solved for, t 105 over 580 equals e to the kt. The natural log of both sides gives me the natural log of 105 over 580 equals just straight out kt, and the natural log of 105 over 580 divided by that value we found for k equals t. Again, doing this kind of inside out, I'm going to say the natural log of 480 over 580. Divide that by 8. Then I am going to take the natural log of 105 divided by 580, close those parentheses, and divide by my answer. And I'm going to get about 72 minutes. 72 minutes. And I guess I could have put in a 72.25. 75 and a quarter minutes. Sounds about right to me. Okay. Okay, here's something which is specifically a logistic model. You will notice that it rises for a while, and it kind of looks like an exponential curve, and then it levels off. This is how most populations actually work. You've probably in biology heard the term carrying capacity and things like that. The population of the Earth in terms of people can only grow so far because the Earth itself only has so much carrying capacity. It can only provide food for so many people and whatnot. Again, this is not an equation that you need to have memorized. It's simply one that you should be able to look at, explore, understand, and manipulate. So let's jump into some examples here. Looks particularly pertinent. The function P of t equals this describes the number of people who have become ill with a virus t weeks after its initial outbreak in a city of 50,000 inhabitants. State the carrying capacity and growth rate. So that carrying capacity is going to be that 50,000 people. You cannot have more than 50,000 people infected. As time goes infinitely far, this is t will be large. That k value is negative. A large value times a negative value is a large negative value. E to a large negative value is close to 0. 60 times 0 is close to 0, and 1 plus 0 is 1. 50,000 divided by 1 is 50,000. So that carrying capacity is 50,000. Growth rate, we're actually just going to leave alone. The only rate I'm interested in is this this k value, this negative 0.9. How many people were initially ill with the virus? Well, in order to do that, I'd be interested in how many had the virus at the time we are designating 0. Well, if t is 0, then I'm taking e to the 0th. Anything to the 0th is 1. 60 times 1 is 60. 1 plus 60 is 61. And clear this, 50,000 divided by 61 is going to be 819. There's a decimal in there, but that's okay. Approximately 819 people. How many people will be ill by the end of the 3rd week? Well, this thing is measured in weeks, so all I have to do is plug in 50,000 over 1 plus 60 e to the negative 0.9 times 3. Can I just call it negative 2.7? Okay, again, kind of inside out. I am going to use the calculator and say e to the negative 2.7. I'm going to multiply that number by 60. I'm going to add 1 to that, and I am going to say 50,000 divided by my previous answer. And I get about approximately 9,936 people. I would never record a decimal person. How long does it take for the number to reach 35,000? So 35,000 equals 50,000 over 1 plus 60 e to the negative 0.9 t. I'm going to start by multiplying both sides of the equation by this denominator over here. And when I do so, I am going to have to distribute. 1 times 35,000 is 35,000. 60 times 35,000. 60 times 35,000 is 210 with another 4 zeros. 1, 2, 3, 4. So looks like we got 2.1 million e to the negative 0.9 t equals that 50,000. I'm going to subtract here, and I'm going to end up with 15,000 equals 2,100,000. Did I get that right? 1, 2, 3. Yep. 2,100,000 e to the negative 0.9 t. I'm going to divide. So on my calculator where I already have the 2.1 million in there, I'm actually going to be a little bit weird and say divide by 15,000. And I get that 140, but I wasn't really looking for that. I was really looking for its inverse. There's an inverse button right there, which will give me the multiplicative inverse, I should say. And I get that e to the negative 0.9 t is equal to approximately 0.007. I'm going to take the natural log of both sides, and I'll get negative 0.9 t on this side equals the natural log of about 0.007. I'm going to say natural log of the answer, and I'll get a negative 4.94-ish. Approximately negative 4.94, and then I will divide by that 0.9. And when I do that, negative 0.9 divided by, in parentheses, negative 0.9, and I get about 5.4 weeks. Okay. Next up, it asked me to use a graphing utility or Desmos. I certainly can do that in order to see when we make it to half the carrying capacity. In other words, when half the population is infected. So I will do that. I'm going to pause again for a second and get that set up. Okay, back at it here. I think I've got this set up so that I can go over to Desmos and hit share. Boom. Okay. So here is in Desmos that equation plugged in, 50,000 over 1 plus 60 e to the negative 0.9. I had to use an x instead of a t. And we have the y equals 25,000. So we can explore a little bit here, and it looks like at 4.5 weeks, give or take, we are at half that carrying capacity. which makes sense. We were well over it at 5.4 weeks. Boom. Okay. We've got other examples here. I don't think there's a whole lot of it worth me going through with you guys on. I'll give you guys the chance to pause it while I do this. I am going to not ask a question like this. What is the decay rate? So please don't worry about that. And I will be back in 1 second. So feel free to pause it as I am pausing it and work this out on your own. Okay, so for the part B there, I got about 98%. So after 10 years, based on the European Forest Institute model, they're still going to have 98% of their wood left. However, after a few more decades and 74.1 years, they're down to 50%. The question at the bottom asks what the numerator really represents. Well, that 100.352 divided by basically 1 when t equals 0. Technically, that 1 plus 0.0136 should give us basically 100%. So they're really saying what are the initial conditions there. It really gives us an idea of what the initial conditions are when I plug in t equals 0. And again, e to the 0th is 1. 1 times that 0.0136 is 0.0136. Add that to 1, divide it from that 100 point something, and we get basically 100% there. Okay, that does it for today. Feel free to email me with questions if you've got them, and let me know what you thought about this. All right, thanks a lot. Bye-bye.